Okay, so now I'm settled down into my desk, answered some emails, wrote some emails, read some emails, started reading an article again, and I was thinking, well, my explanation when I ran into my office and was putting everything away might not have been the most ideal. I jumped directly into mathematics of the whole situation. So I want to give, before I go out to lunch, I'm going to give a little more of a background on why I'm using the models and the equations that I'm using. So what I'm most interested in is crystallization. So crystallization is basically an equilibrium between a solid and a liquid. So if you change that equilibrium in some way, crystallization will occur, or it'll dissolve further. An example is it's like sugar, candy, let's say. So if you have just water at room temperature, you can add sugar to the water, and a lot of it will dissolve. But at a certain point, no more sugar will dissolve in the water. So it's reached its solubility point. It's reached the equilibrium between the solid and the liquid. But if you change this equilibrium by adding heat, for example, if you heat up the water, the rest of the sugar will dissolve. In fact, sugar at the higher the temperature, the more sugar you can put in. So if you want to make candy at home, what you do is you boil water and you add just per liter, like a kilo of sugar, maybe even more. It's very, very soluble at high temperature sugar. And when it cools off, it will crystallize. And you can shape it in the way that you want. You can make like candies or anything. So an important application of my work and the work of many people in this area is pharmaceutical industry. For example, they want to make a medicine, and they develop it, and you make it in solution. So when the upstream production of any pharmaceutical is almost always in a liquid form. But you have to ask yourself, would you rather have a shot or a pill? Yeah. So if you have a headache, do you want to go to the hospital and have them give you a shot, or would you just like to take a pill that you can buy over the counter? And it's not just for headaches, chemotherapy. Do you want to go every time that you get chemotherapy because you have cancer, for cancer therapy? Would you want to go to the hospital, or would you just like to take a pill? There are many advantages of pills. Not just the ease, of course, that's a very large part of it, but stability. Crystals are very, very pure. You can be pretty sure of that. And if it's in a liquid, you may have some impurities. It's easier to have an impurity in a liquid form than it is in crystal form. Furthermore, I don't know furthermore. I'll just continue. So you have more purity. Oh yeah. Obviously, it's easier to store. Medicines in liquids are very sensitive to temperature and light, etc. But if you have it in a pill, you can store it quite easily. So that's one of the applications. But let's also talk about costs. Pills, medications are not cheap, and crystallization, purification in any form, even if you keep it in the solid, purification is extremely expensive. The downstream processing of pharmaceuticals, but also foods, are 90% of the total costs of production. So if you can find very efficient ways of purifying, for example, crystallization, then you just by 1 or 2%, you can save billions of dollars on the production of pharmaceutical. So that's the application of my work. I look at this equilibrium between the solid and the liquid. Specifically, I'm looking at a group of biomolecules I'm not really supposed to tell you about. I've been asked not to be too specific about which molecules I'm working on. but I'm not only working on these molecules separately, but also in a mixture, which brings a very, because if you're trying to purify something, you have other molecules in the way of that crystallization, and they have a big effect. So that's what I'm working on. Now I can go back to the formulae that I showed on the board. So what the industry needs, what you need when you're doing a production, is the activity. The activity of a molecule is independent of temperature, and that's something that you want to know for anything. So I'll turn around. That's actually down here. That's what we eventually want to get to. We want to get to the activity and infinite solution of a molecule. Which you work backwards. Here we are. Here is the activity. The activity is the ratio of the fugacity between the solid and the liquid, because I'm looking at solid-liquid equilibrium, crystallization. It's the derivative fugacity. The problem is the fugacity of a liquid can be calculated by the vapor pressure. However, and the thing is that I'm looking at, on the first side, some of them you can. You can actually measure the change in fugacity of the vapor. However, some of them are very insoluble, so there's no way of really detecting the change in vapor fugacity of these biomolecules. Secondly, the second problem is I'm looking at mixtures. So even if I did measure the fugacity of the mixture, I don't know the individual fugacities, so that doesn't help me. The other thing, you can also calculate the fugacity of the solid. That's the article actually right now I'm reading, and this was developed by the gentleman, Professor Prausnitz, which I'm going to see in a couple hours. So to get this ratio, the fugacity of the solid to the liquid, there are a couple of ways you can do it. First of all, you need to measure this X, that's the solubility of the molecule in the solvent, so like water or ethanol or methanol or isopropanol or whatever solvent that you are using. And then you have to have the activity coefficient. Well, that's the problem. The X, I spent 2 years meticulously gathering data in the laboratory. You can do that. It just takes a long time, but you can measure this. The activity coefficients, you cannot just measure an activity coefficient. There are two basic ways. Either you can use the UNIFAC equation, which is, if you think that equation is complicated, it's an equation based on the group contribution of groups of molecules can be made of different groups, and for each group it has a certain physical chemical properties, which you can then use this UNIFAC formula to calculate coefficients, activity coefficients. The problem is, this is what I ran into, is that now, okay, it's complicated, but that's just a matter of mathematics. That's not that big of a deal. I like that. But the interactions between the groups, it's missing a lot of data. And for at least half of the molecules that I'm interested in, it's missing the group interactions. So I can't use the UNIFAC. The other way to get the solubility of that, the solubility coefficient, activity coefficient of saturation, is using the Lorero and Gani estimations. And then using their formulae and their method, you can then estimate the enthalpy of fusion of these molecules and the melting temperature, because as I mentioned, the molecules I'm interested in are they don't melt, they disintegrate, and also they don't have really an enthalpy of fusion that's measurable. So you have to estimate that. Thankfully, people have already done that for me. I've been able to find that data. So it just took me a couple of days of finding all the data that I needed. And now with all this data, I can finally calculate, because I measured this, I can calculate that, and I figure out what that is. To then get the A, which is this ratio, and then find the activity at infinite solution. So that's what I'm working on now. Once I get that, I can also calculate the fugacity of the solid, and then publish it.